Okay, problem 1 on your handout. We have one sample of 25 workers. For that group of workers, the sample mean is 106 with a sample standard deviation of 15. And I have summarized that information right here. Can we conclude that the population mean is greater than 90? That's our research hypothesis, mu greater than 90. And I'm going to go ahead and ask here if the sample size is large enough to guarantee a bell-shaped sampling distribution for the sample mean. The sample size is 25, which is okay as long as there are no outliers or extreme values. At the very least, you should draw a box plot if you had the data here. We don't right now, but if you had this data, you would draw box plots to see if there were outliers or extreme values. Of course, if you knew that in the population those were likely to occur, you would have presumably drawn a larger sample size to begin with. Okay, I'm going to compute the test statistic here. That is the statistic minus the hypothesized parameter over the standard error. X bar was 106, the hypothesized mean was 90, sample standard deviation 15 divided by the square root of the sample size. That gives us 5.33. That means this has the same interpretation as a z-value, that our sample mean is 5.33 standard errors above the hypothesized population mean. If you remember all the way back to the empirical rule, when you've encompassed about 3 standard errors or 3 standard deviations, you have close to all of the data. Therefore, we can already go ahead and see here. Therefore, we can already, I think, conclude that our population mean really is greater than 90. But we'll go through all of the steps here. So for the p-value, since this is a t-test, I got that p-value from my calculator. It was 0.50896. So if the population mean is 90, and you can see that I have that, go back there. There's the population mean of 90. There's the statistic that's being observed. And the standard error in this problem was 3. That was that 15 divided by the square root of 25. And I have that depicted here. That's 1 standard error. That's 2. That's 3. And the 106 that we found out here, remember that was about 5.33 standard errors above the mean. So it's way up here. But anyway, if the population mean is 90, if HO is true, then there is a p-value chance, very small in this case, of obtaining a sample mean greater than or equal to 106. So that's the general statement that you should always have when you're interpreting the p-value. In the context of this problem, we'll reject HO if the p-value is less than 0.05. It is, so we will reject HO and conclude that the population mean, mu, is greater than 90. So for our confidence interval, we will have the statistic plus or minus the confidence coefficient, which is t, because we have sample standard deviation. Remember, S and T are next to each other in the alphabet. They go together. Sample standard deviation goes with the t distribution. And then divide by the square root of n, you get the standard error. That's what all of this is. S divided by the square root of n is the standard error. That's where I had the 3 on the previous slide. So the sample mean, this is 1.711 with 90% confidence and degrees of freedom equal to 7. Degrees of freedom equal to 24. That's 25 minus 1. Look that up on the t-table. You'll get 1.711. And now we just have our calculation here. So our interpretation of the interval is that if we have repeated sampling, all of our interpretations of confidence interval are based on the idea of repeated sampling. We're 95% confident that the interval we computed is one of the intervals. Again, we are really only going to compute one interval, but our statement is about the method wherein we would, at least theoretically, repeat this process over and over again. And if we did that, 90% of the confidence intervals would include the true population parameter, in this case the true population mean, and 10% wouldn't. So we're, I guess, in a sense, betting and having a 90% chance that the interval that we computed is one of the intervals that really did have the true population mean. So in the context of this problem, now we're going to get it in the context of this problem, the entire interval is above 90. Therefore, we can conclude that the population mean mu is greater than 90. Okay, for the one sample t-test, just hit stat, tests, t-test, enter. If you have statistics already given in the problem, make sure you have stats selected up here. If you actually had the 25 numbers, you could put those in a list and refer to the data. But we just have the summary statistics given in this problem, so we'll select stats. Then the mu0, that's my hypothesis. The 0 stands for null, so 90. The sample mean and the sample standard deviation and the sample size, those are just straight from the problem. Then my research hypothesis, the mu, then you get the colon. We have a one-tailed upper, so it's greater than there. I've already entered those in, so I'll just go down and hit calculate. And there's the t-test value of 5.33. And the p-value says 8.95. Now the p-value has to be between 0 and 1, but if you look over here, you see exponent, or e, to the -6. So you'll have 5 zeros and then the 8955, whatever there. For the confidence interval, stat, tests, and for the 1 and 2 sample cases, the confidence intervals are all down below the hypothesis test. So I'll go down to the t-interval, hit enter. Those numbers will already be in there except for the confidence level. And you can put that is a decimal 0.9, or you could just enter in 90. I usually just enter in the 90 and calculate. And you can compare that to the confidence interval we calculated. If it's off at all, it'll be off a very little because of rounding. So for problem 2, we're looking at stress measured before and after taking a statistics exam. So for example, with Allie, before the exam, she had a stress level of 19. After the exam, that had reduced by 3 to 16. We're going to look at differences in terms of before minus after. My research hypothesis is going to be that the population mean mu of the differences, you'll see what I mean by that in just a moment, is greater than 0. N is equal to 8, so we're large enough only if we're sampling from a normal population. Let me just say that that we're doing now a matched pairs t-test, or a paired t-test. Keyword in there is paired. And that our hypothesis will always have a 0 in it. HO is always equal to 0, and HR will depend on how you subtract over here. What we're really going to be looking at, our x variable now, is going to be differences. For Allie, before minus after, we're saying she was higher by 3 before. And for Beth, -2, Hannah 0, Morgan 4, and so on. So we're saying that these differences were higher before, and that's why I have mu greater than 0. You could have subtracted the other way, in which case you would have minus signs, and then that would be mu less than 0. So it depends on how you subtract, or the direction of your subtraction. So now you can see that I have computed all of those differences. And again, my hypothesis is that the mean, the population mean of differences, will be greater than 0. There will have been stress relief, that the stress was higher before than after. Okay, so for the matched pairs t-test, or again, paired t-test, we'll need to compute the sample statistics. Let me come back and say that those differences, which we just computed on the last slide, that's our x now. You can forget, after you've gotten those differences, you can forget the numbers that were in the before and after, or pre-test and post-test, whatever it is. We're just looking at the differences. So we add those differences up, get 16, divide by the sample size of 8. So our average difference or change is 2. Subtract that from each value to get the deviations. 3 minus 2 is 1, minus 2 is minus 4. Square those deviations. 1 squared is 1, minus 4 squared is 16. Add all those up. That's 58. Divide by n minus 1, 8 minus 1. Take the square root, and you'll have a standard deviation of 2.878. That's the standard deviation of these differences over here. Our test statistic is equal to the sample mean, that's 2, minus the hypothesized mean, which is 0, divided by the standard error, which is the standard deviation divided by the square root of n. Notice that once we have the differences in the calculation of the statistics in our hypothesis, this is exactly the same problem as the one sample t-test. Now in many texts, and you'll see on the formula sheet that I've given you, people will put this as d bar minus the mean of the d's divided by the standard deviation of the d's. And that's all fine and good, but I'd like to emphasize, and that's why I'm using x's, that once we have formulated the hypotheses and let x equal the differences, compute the statistics, this is exactly the same problem as the one sample t-test. So now our p-value, which I'll get using the TI calculator, either an 83 or an 84. And I'll show you how to do that in a moment. Our p-value is going to be 0.045, so that means that this is 0.045. So again, just to go over the graph here, whatever the statistic is the label for the x-axis. That's the null hypothesis. Here's the statistic that we observed, and it's on the scale right here. So when we interpret the p-value, we'll say if the population mean is 0, if HO is true, then there is a p-value chance, whatever we have out here in the tail that's shaded in, of obtaining a sample mean, a statistic, in this case a sample mean greater than or equal to 2. So we're really just putting this graph into words. The population mean is 0. If HO is true, there's a p-value chance, so we have shaded in, of obtaining a sample mean, x bar, greater than or equal to 2. Putting this in the context of this specific problem, we'll reject HO if the p-value is less than 0.05. It is, so we will reject HO and conclude that the population mean, or the population mean of the differences, is greater than 0, that there has been a change, that the stress level has gone down. It was higher before than it is after. So the 90% confidence interval is the statistic, x bar, plus or minus the confidence coefficient, t, times the standard error. Most of that is just plugging in 1.895, we have degrees of freedom of 7. There were 8 observations there, 8 minus 1 is 7, and 90% confidence. So just go to the t-table. This will be in the first column of coefficients. Go down to 7 degrees of freedom and read across there, and you will see 1.895. Calculating that out, we'll get 0.0718 to 3.928, and our confidence intervals for the paired t-test will compare to 0. That entire interval is greater than 0. Therefore, we can conclude that there is a difference somewhere between 0.07 and 3.9. So interpretation, again, we're back with the repeated sampling. All of our interpretations of confidence interval involve repeated sampling, and we're confident that the interval we computed is one of the intervals of the many that might possibly that includes the true population mean, which we really don't know the true population mean. All we know is that if we kept constructing intervals, 90% would include the real population mean. In the context of this problem, as I said a moment ago, the entire interval is above 0, so we can conclude that the difference is greater than 0, and we're confident that the stress level was higher before the exam than it is after. Okay, for the matched pairs t-test, or paired t-test, I'm going to give you a couple of ways to do that. Sometimes one's easier, sometimes the other. Stat, test, t-test, and here I've just entered the hypothesis of 0, the sample mean and sample standard deviation. Now, if I already have the sample mean and standard deviation, this is probably the way to go. Then the sample size of 8, I've got not equal, then I have greater than there, and then calculate. And there's my t-value and my p-value, and so on. To get the confidence interval for the t, I just go back to tests, down to t-interval. If I've already run the t-test, the interval's still going to be there. Might have to change the confidence level, but not in this case, and hit calculate. And there's your confidence interval. Again, if it's not exactly what we had when we worked it out by hand, it should be pretty darn close. Could be a little bit of rounding error. Okay, I told you I'd give you another way to do the matched pairs t-test, and if you don't already have the mean and the standard deviation, this one can save you a little bit of time. Especially if you're doing this for a multiple choice or something where I tell you you can use the full power of your calculator and you don't need to show work. So, stat, edit. And now what I have done is in lists 1 and 2, I've entered the numbers from the problem. For example, Allie was 19 before and 16 after on the stress test. So I've just done that for everyone. Now I'm going to go over to list 3 and highlight the L3 at the top. Then I'm going to have second 1. You can see down here now I have L1, that refers to list 1, minus second 2, that's list 2. And remember, when we computed the differences, we took the numbers in this column and subtracted the numbers in the after column. That'll do it for you. So there are the numbers that we had for differences. So now we can hit stat, tests, t-test, and instead of asking for stats, instead of inputting stats, we'll input data. We still had a hypothesis of 0. Now we need to change this to list 3. Don't change the frequency thing. That was greater than, leave that alone. And there's your t-value of 1.96 and your p-value of 0.045. We can do that for the confidence interval as well. Just go to stat, tests, t-interval. Now all we have to do is make sure we have the confidence level correct, and I believe we do. And that'll be that. So for problem 3, now we move to a case, the difference between sample means, where we have two samples. A sample of 25 gas stations within 1 mile of the interstate, which has a sample mean of 265 and a sample standard deviation of 0.24. And then we have a second sample, another sample of 25 gasoline stations. Now these are more than a mile away, and they have a sample mean of 2.52, sample standard deviation of 0.28. You can take note here that I also went ahead and computed the sample variances. That's just going to help when we enter numbers into the formula in a minute. So I took the 0.24 and squared it to get 0.0576, and the 0.28 and squared it to get 0.0784. Our hypotheses now, our HA alternative, which is the same thing as HR, is that the two population means differ, that mu A is not equal to mu B. HO is that the two population means are equal. I'm going to restate HO here, the null hypothesis, as mu A minus mu B is equal to 0. Of course, if the difference is 0, they're equal. I'm doing that because when we get to the sampling distribution, we'll need to know where we put the center of the distribution, and it will be centered on 0. Sample sizes, don't combine them. Look at one sample size, 25. If the sample sizes were different in size, you pick the smaller one. So we have 25, skew's okay, outliers or extreme values are not. So our test statistic is equal to the difference between the two sample means, that's our statistic, minus our hypothesized population parameter. Should have put an H right here. Some people put a 0, which stands for null. But again, statistic minus hypothesized parameter divided by standard error. So I've just plugged down here. Make sure you put in variances. That's why I calculated variances on that first page, just to make it easier when I enter the things down here. And that all comes up to be 1.76, which means that this statistic, the difference between the two sample means, and really it might be better here, I've done this 2.65 minus 2.52, to think of that as one number, 0.13, just the difference, minus the hypothesized difference, which will always be 0. So this 0.13 is 1.6 standard errors above 0. I think I'll go ahead and mention here, you'll see in many books and on the formula sheet that I have, I'm just going to leave it in there, two different formulas for standard error. We'll just use this one for this course. You'll note that it's a little shorter than the other formula, and this is the one that our particular text that we're using right now recommends. Other texts actually use the other one or use both under different conditions. It depends on the relative size of these two variances. But for us, we'll just say that we'll use this one, and you'll see when we get to our calculator that this is going to be what's called the unpooled measure. And on your calculator, when we get to where it asks if you're pooled, you'll just say no. Okay, so our 95% confidence interval is the statistic, the x bar A minus x bar B, plus or minus the confidence coefficient T, times the standard error. So again, we have that 0.13, 265 minus 2.52, times a t-value, times the standard error. Now I'm going to go ahead and tell you that the degrees of freedom for this one is 46, and we'll get that from our calculator, and I'll show you in a moment how we get that on our calculator. But for now, just keep in mind that the degrees of freedom here, if you want to go ahead and look it up, is equal to 46. Well, anyway, then we get our interval, and it is minus 0.0185 to positive 2.785. That interval includes 0. That means it's plausible that there is not a difference between the two population means. And of course, we also have our ever-present interpretation of confidence interval based on repeated sampling, 95% confident that the interval we compute is one of the intervals that might be computed, one of the many intervals that might be computed, but our interval we're going to be 95% confident is one that really does include the true difference between the two population means. Again, this 95% refers to the method, not to a specific interval. Okay, here's our p-value, and our p-value turns out to be 0.0845, which, since I have a two-tailed test, is the total area in the tails of the distribution. Let's also go ahead and look at how we have this thing labeled. The statistic, x bar A minus x bar B. The hypothesized parameter, and this is why I, instead of just saying mu A equal to mu B, that's why I restated that as mu A minus mu B is equal to 0. That's the center of the distribution. And I have the standard error here. I'm just going to give you that. It's 0.0738, and you can see then that that's one standard error, two standard errors, and we're not quite two standard errors away in this particular problem. This is a little bit tricky saying what the p-value means, or a little bit trickier for saying what the p-value means when you have a two-tailed test. It's still if HO is true, if mu A is equal to mu B, or if mu A minus mu B is equal to 0. I just put it in words here. If there's no difference between the population means, then there is a p-value chance of obtaining, and for the two-tailed test, of getting a difference between sample means, that's x bar A minus x bar B, greater than or equal to 0.13, or looking at the other side, now we're going to have minus 0.13, the same distance from the mean that we had over here. Going this way, we had a difference of 0.13 minus 0. So going the same side here. So again, that 0.0845 p-value refers to above here or below here, which is what we have shaded in. So the second thing is a difference between sample means less than or equal to minus 0.13. Then just into the context of this problem, 0.0845 is not less than 0.05, so we fail to reject HO, that's what that FTR is, fail to reject HO, and conclude that there might not be a difference. It's plausible that HO is true. For the two-sample t-test, stat, tests, two-sample t-test, I'm inputting statistics. So far, these are just the numbers from the problem. X bar 1 was 2.65. Make sure you enter standard deviations and not variances when you're using the calculator. So not the 0.0576 variance, the 0.24, which was the standard deviation. This was a two-tailed test, not equal to. Pooled, we're going to answer no. And then calculate. There are some videos where I make a distinction between the pooled and the unpooled, which we have no. But the text we're using this fall only does the unpooled. And I think given that the actual differences sometimes or usually are not that great, that's fine just to do it one of the ways. If you get into some more advanced stat, you can get into the difference between those two. But enter, there's your t-value and your p-value, just like we had before. And then for the confidence interval, stat tests to samp t interval. Everything's already in there. The only thing that might change is the confidence level. That was 95. And we'll calculate. And then there's the confidence interval. I think when I did that by hand, I got minus 0.0185. But again, there's a little bit of rounding in there. Anyway, I told you also, and this was on the other one too, the degrees of freedom I gave you when we worked it by hand was 46. You just have to lop off any decimals on this. There's a big formula that calculates this, and it frequently gives you decimals here. Just lop them off. Always round it down. Let me go back and show you where that was on the test, to sample t-test. Right here. Degrees of freedom, 46.9. Round that down to 46 when you're using the t-table. Okay, so problem 4. This is a 1 proportion z-test, the same kind that we've seen before. We have a sample size of 500. 230 have met the minimum recommendations. Sample size, we had 230. Yes, 270, that's 500 minus 230. No's, both greater than 10, so n is large enough to guarantee a bell-shaped sampling distribution. This is enough evidence to conclude that the population proportion, that's P, is less than 0.5. So that's our HR or HA for alternative, whichever way you want to call that. Some books also call it H1. Put what you want to conclude there, and then HO always has an equal sign in it, P equal to 0.5. So I went ahead down here and computed the sample proportion, just X divided by N, 0.46. For the confidence interval, take the statistic, the 0.46, that's P hat, plus or minus Z. All of the problems involving proportions will use the Z table, times the standard error, which is P hat, which is 0.46, times Q hat, which is 1 minus that, or 0.54. The 1.645 is a Z value. You can get it from the Z table. It's a little bit easier to use the T table I gave you and just go down to the bottom row on the back and read the row that says Z. That comes out to be 423 to 0.497. That entire interval is below. That should be 0.5. Must have had a space in there. Anyway, the whole interval is below 0.5, so we can conclude that the population proportion is less than 0.5. Again, we have our normal statement there about the repeated sample stuff. You can read that. I'm not going to repeat that here. Our p-value for the proportions, since they're z-tests, we're going to go ahead and show our work for that. We take the statistic, all of our hypothesis tests, all of our t-tests and z-tests are equal to the statistic, in this case p hat, minus the hypothesized parameter, in this case pH, divided by the standard error, which for proportions and hypothesis testing is pH, the hypothesized proportion, which was 0.5, times 1 minus that, divided by n. You may recall that for confidence intervals and hypothesis testing for proportions, the standard errors differ slightly for hypothesis testing and confidence intervals. We get a z-value of 1.79. Look that up in the z-table and find an area of 0.4633. Again, that's from the mean to this point. So we'll subtract that 4633 from 0.05 to get 0367, and that then is our p-value over here. So again, for the labeling, for the x-axis we have our sample statistic, in this case p hat. The center of the distribution is p equal to 0.5, and then we have our standard error, which is just what we have in the denominator here. I don't know that it's worth calculating all of the time, but at least in terms of showing you a little bit about what we have here, there's one standard error, see 0.5 to 0.522, 2, and 3. 1, 2. You can see we're not quite 2 standard errors below. In fact, we are 1.79 standard errors below. And then here is the specific value of the statistic that we have in this case, the 0.46. So make sure that at a minimum you have the bell curve, that it's labeled with the p hat, with the hypothesized proportion in the middle, and the specific value of the statistic located on the curve, and with the p-value shaded in. If you're in the web class, what I might do is give you a problem where I draw 3 or 4 sampling distributions and ask you to select which one is the correct sampling distribution for a particular problem. In the classroom sections, you just need to be able to draw it. Okay, so that p-value was 0.0367. Again, this is just the same stuff up here, the same formula, and the same curve that I had on the previous page. Just wanted to get to the interpretation. If HO was true, p is equal to 0.5, then there is a p-value chance, 0.0367, that the sample proportion, that's what we have drawn on this, that we get a sample proportion less than or equal to the 4/6 that we observed. In terms of context, we reject HO because the 0.0367 is less than 0.05 and conclude that the population proportion is less than 0.5. For the one proportion z-test, stat tests, one prop z-test, and we had a p0 of 0.5, an x of 230, an n of 500, and we were doing less than, and then calculate. You'll see there's our z-value of minus 1.79 and our p-value of 0.036. I think we had 7 maybe when we did it by hand. That's because the z-value is actually a little less than 1.79, and the calculator does all the interpolation and so on. For the confidence interval, stat tests, one prop z interval. We just need to make sure we have the confidence level set. And there we go. Remember, this was all less than 0.5, barely, but all less than 0.5, so we were confident that the population proportion was less than 0.5. So now we come to problem 5, and in this one we have another problem with proportions. But now there are 2 samples, males, which I'll call group A, and females, which I'll call group B. And at least here, we're just getting the information for males, sample size of 100, 74 of whom say it takes over a week to recover from daylight savings. Glad to know that that's coming up again soon. I'm one of those males that take over a week. Hopefully I can do it in under 2 weeks this time. Our sample proportion then for males will just be that 74 divided by 100, or 0.74. Same thing over here, but for females it was 66 out of 100, and the sample proportion was 0.66. In one of our formulas we're going to need something called the pooled proportion. The reason we need it is when we draw our sampling distribution and when we do our p-value, we're assuming that HO is true. And HO was going to be that the two proportions are equal. If that's the case, then we really can think of this as one large sample instead of two separate samples. So in our total sample, we take 100 here and 100 here. That's 200. That really should be a small n. And for the number that said yes, we take this 74 and add the 76 to get 140. And then this is the p-bar or pooled proportion, which will be the 140 divided by 200, or 0.7. If these two sample sizes here are equal, the 0.7 is just the average of the 0.74 and the 0.66. If the sample sizes are not the same, then they won't just be the simple average. For example, if we had 200 females and 100 males, the females would be weighted more heavily in our calculation of p-bar than males would be. So in Group A, we had 74 yeses and 26 noes. Group B, 66 and 34. All of those are greater than 5. Therefore, our sampling distribution, the sampling distribution of the p-hats, remember sampling distributions are distributions of statistics, whether it's p-hat or x-bar or x-bar A minus x-bar B. The sampling distribution is the distribution of the statistic, the z distribution, or for means, the t distribution, without knowing the real shape of the population. I don't know if you can hear that. That's my dog. Apparently a little upset about something. So our hypotheses, we want to know if the population proportion for Group A, for males, is higher than it is for Group B, females. And so HO is, of course, that they're equal. Like means, it's also worth saying here that PA minus PB is equal to 0. Another way of stating the null hypothesis. So our p-value, since it's a z-test, we can compute a z-value and then just go ahead and use that to calculate the p-value and show all of our work. We have the statistic, the difference between the two sample proportions, p hat A minus p hat B, minus the hypothesized parameter, PA minus PB hypothesized, divided by standard error. You can see here where we're calculating the z-test, we're going to use the pooled proportion of 0.7 and 1 minus that of 0.3. And then there's just 1 over our sample sizes. So anyway, there's all the numbers entered in. Calculate that out and you will get a z-value of 1.23. That means our sample statistic, the difference between sample proportions, is 1.23 standard errors above the hypothesized difference between population proportions, which will, for our purposes, always be 0. So again, there's just all those calculations again. We had a z of 1.23. We look that up in the z table, we'll get 0.3907. That will be this area. That's 3907. Here's our p-value, and that will be 0.5 minus 0.3907, or 0.1093. Again, to get this all drawn and looking right for the sampling distribution, we have our statistic, we have our hypothesized parameter, that's why I took the difference to get 0, and we have the specific value that we have for our statistic. That's just the 0.74 minus 0.66 is 0.08. So when we're drawing these curves, it's a distribution of one number, the difference between sample proportions. So that's about right there, about 1.23 standard errors above the hypothesized parameter. If there's no difference between the population proportions, if HO is true, then there is a p-value chance, that's 0.1093, of getting a difference between sample proportions as high or higher than that we observed. We'll fail to reject HO. 0.1093 is not less than 0.01, and we will then conclude that it's plausible that HO is true. And now for the confidence interval, the statistic, p hat A minus p hat B. I'm going to put parentheses there just to emphasize that you should think of that as one number, the 0.08, plus or minus the confidence coefficient. You can get that off of the Z table or the bottom of the T table. Just go 98% confidence and look right above it. You'll get 2.326 times the standard error. That's the same in both of these. I just rewrote it to emphasize that that's one number. And we'll get minus 0.07 to positive 0.23. That interval includes 0, which means that the two population proportions could be equal. Again, looking for 0 in the interval works for all three of the new problems. The match pairs t-test, the two-sample t-test, and the two-proportion z-test. Look to see if the interval includes 0. If it includes 0, they may be the same. If it doesn't include 0, then we can be confident that there is a difference. Okay, that's what I just said there. And then here's our, hopefully by now, routine statement about repeated sampling. We're 98% that our interval is one of the intervals that really includes, in this case, the true difference between population proportions, or between the two population proportions. For the two-proportion z-test, stat, tests, two-proportion z-test, x1 was 74, then we had out of 100, then we had 66 out of 100, and we said greater than, and calculate. There's that z-value of 1.23 and a p-value. Again, it's a little bit off because we used the z of just exactly 1.23, and it's actually a little higher than that. To get the confidence interval, stat, tests, two-proportion z interval, everything's in there. I think we even had 90% on that. And there we go. No, we had 98% on this one. Stat, tests. So change that to 98. Then calculate. There it is. That's what we had when we worked this out.
That's all, folks.